Welcome to the fourth day of summary school on algorithm. And today we have Professor Meghana from IIIT, from IIT Madras. She is an assistant professor in the Department of Computer Science and Engineering in IIT Madras. She did her undergrad from NIT Nagpur and postgrad from IIT Bombay. And she received her PhD in graph algorithm from IIT-Bangalore. Her research area include graph algorithm, matching in graph. And she will be giving talk on stable matching. So we welcome you, Professor Meghana. Over to you.
Thanks a lot, Avi. And I thank all the organizers of the school for inviting me for this talk. I hope the participants are enjoying the sessions, although they are virtual. We have had such workshops in person, and we also had the pleasure of meeting students, but now everything has moved to this virtual mode. Okay, so so I see several participants who have joined in. So good morning, everybody. And as Avi has mentioned, my name is Meghana Nasre. I work at IIT Madras, and my area of interest is graph algorithms and matchings in graphs. So what we will be talking about is a particular problem in matchings called the stable matching problem. And we'll also try to relate it to things that you have seen earlier, in particular some parts about approximation algorithms that you have seen, and we'll see it applied to this problem, which is the stable matching problem. So during the any time during the talk, feel free to interrupt me if you have questions. The whole talk is elementary. That is, it means that everything that we are going to do is from first principles. So anytime you do not understand anything, stop me. It is most likely that I am not explaining it correctly, than you have missed out something. Okay, so let's begin with the problem setup. So we have, we'll have a bipartite graph underlying our, which is representing our problem. And the one side of the bipartition, we'll call it as A. This A represents in real life either applicants, students, medical interns. Throughout this talk, we'll be calling them as men. That is the classical way the problem is defined, the stable marriage problem. Then the other side of the bipartition, we will call it as B, which can represent jobs, courses, or hospitals. These are corresponding things. That is, applicants need to be assigned to jobs, students need to be assigned to courses, medical interns need to be assigned to hospitals, and so on. So these are the two partitions that we have, A and B. These are the two sets, that is, or the set of vertices that we will have. And each participant has a preference ordering over the set of acceptable people from the other set. So we'll see an example soon. So the preference ordering says that, let's say there is a participant A1, which we'll call it as a man. Then A1 has ordering over all the B's that is acceptable to the person A1. And it says that B1 is, let's say B1 is the top choice, B3 is the second choice, B4 is the third choice, and some B's may not be acceptable to that person A. So, for example, in our small instance, we have two A's, that is A1 and A2, and two B's, which are B1 and B2. And this, the thing that is shown beside is called the preference ordering of A1. That is, A1 prefers B1 over B2. It's also typical to write a comma in between, but I have omitted that. And A2 also has the same preference list. That is, A2 also prefers B1 over B2. So this is how the preference list is there for A1. B1 has a preference list of its own. B1 has a preference list which is A1, A2. In this example, B1 and B2 both have the same preferences. This may not be true, and we will see examples of this in future. So when we say that every vertex or every agent or every man and woman have preferences which is a linear ordering, then we say that it is a strict preference list. That is, a person cannot say that I have a B1 and B2 both at the same rank, or I like both B1 and B2 equally. If you do not allow such things, you say that the preferences are strict. And if you force that every A should rate all B's that are available, then you call the preferences as complete. So this is what is called as the classical setting, which is called as the classical problem, or the classical setup of the problem, where the preferences are considered to be strict and complete. And what is our goal? Our goal is to assign these men, that is the A's, to B's optimally. So we don't want any assignment. We want to assign them optimally, and we will define what optimally means. So at this moment, I have stated the input to the problem. I have not specified the goal completely, but we will come to that goal. But before that, I want the participants to say that whether they have seen this problem earlier, so that I get an understanding of how to go about it. So I see some chat messages. Okay, so Mrinal says that she or he, I do not know, has seen the problem earlier. Yes, meaning I assume that you have seen the problem earlier. Okay, 2 people have seen the problem. Okay, great. So I see that many people have seen the problem. At least 5-6 students have replied that they have seen the problem, which is very good. Then I can speeden up some of the things and spend time on things which possibly are new. Okay, so if it is possible, I would also like people to unmute and interact, so that this becomes a little bit of interactive and interactive session. So I would like to know what all have, so somebody who has seen the problem, what all do you know about the problem? Feel free to interact. The answer, there's no single answer to this. There's no correct answer. Whatever you have seen, you have to say. Okay, so people are not yet willing to open up. Okay, so Gale and Shapley algorithm you have seen for the problem. Very good. So anything else that you have seen about the problem? This one person has responded. Hall's marriage theorem. Okay, great. So Hall's marriage theorem is not directly used. We are not going to directly use it here, but it's very relevant to matchings in graphs. So that's very good. Okay, so what we will do is, I think there is a large portion of students who have not responded. So I am not sure whether they have seen it or they are aware, but we will go slow and we will make sure that everybody is in the same pace. So what we are going to do is, in this next slide, you see that there are some A's, and in the A's preference list, I have also marked some B's. That is, I have squared out some B's. And this is what I propose as an assignment of A's to B's. So every A is interested in getting matched to one B, and at most one B, and every B is also interested in getting matched to one A. That is why it is called as the stable marriage problem in the classical setting. So let's see that this is a candidate assignment. It is a valid assignment. Now let's see whether it is optimal according to what we would like, or what is with respect to the preferences. So we haven't defined what is optimal. We will call this assignment as a matching. It is a subset of the H set in the underlying bipartite graph. If you are able to view this, this is a complete bipartite graph, which is a 2 cross 2. And in that we have selected 2 edges, which are given by A1, B2 and A2, B1. Now, we will define the notion of optimality, which is the notion which is called as stability, and we will define it as follows. So a pair AB, which is belonging to this H set, which is the H set E minus the matched edges. So I'm always going to talk about a blocking pair or an unstable pair with respect to a matching M, and the matching M is given to us. So some matching somebody has produced for you, or an assignment of A's to B, we'll call that as an unstable pair if the following conditions hold. That a matching, we will call a pair AB, we'll call it as an unstable pair with respect to that matching if the following conditions hold. That is, both A and B prefer each other to their current partners in M. If this condition holds, then we will call that the matching is matching has this blocking pair or an unstable pair, and therefore that matching is not a stable matching. So in this example, with respect to the given blue matching, we have a pair which is A1 B1, which we will, if we view this, then we see that A1 prefers B1 over its current partner, which is B2, as well as B1, which has been assigned the partner A2, also prefers A1 over its current partner, and therefore both, the pair A1 B1 is a blocking pair, or we say that it blocks the matching M, and therefore this matching M or an assignment is unstable. Right? So is the notion of a blocking pair clear if you have not seen it earlier? If you have seen it, then it is just a quick refresher. Is there any question about the blocking pair? Okay, so I assume that it is clear. So a matching, as I said, a matching is stable if there is no blocking pair with respect to it. So if we are given an instance of this problem, that is a set of vertices A, a set of vertices B, then if we are interested in finding and a matching M, we can easily check whether the matching is stable or not by looking at all the unmatched edges and asking, do you block this matching? Do you block this matching? So I would also like to say that if you check this pair A2 B2, which is not a matched edge with respect to this matching, then we ask A2. A2 does not like to deviate, or A2 does not prefer B2 over its current partner. What about B2? B2 has got A1, so B2 also doesn't like to deviate. So A2 B2 is not a blocking pair with respect to this matching. So all edges which are unmatched need not form blocking pairs. Even if there is one edge which is unmatched, which blocks the matching, we'll call that matching as an unstable matching. Okay, great. So this is the notion of stability that we will use as the notion of optimality with respect to preferences. Okay, good. So in fact, in this instance, there is another matching which is very simple, which is A1 B1 and A2 B2, which is a stable matching. Note that everybody does not have to get their top choice. A2 gets matched to its second choice, yet the pair A2 B1 is not a blocking pair because B1 has got a better choice, which is A1. So A1. So in this instance, there is a matching which is stable, which is M prime. Okay. Yeah. So what we know is that if you have this classical setup where you have n men and n women, or the underlying bipartite graph has two equal sides of the bipartition, then and the preference lists are strict and complete, that is what we had defined earlier, that is a linear ordering on the neighbors of every vertex, and the preference lists are complete, that is the underlying bipartite graph is a complete bipartite graph, then the following things hold, that is every instance admits a stable matching. It is not immediate if you are looking at the problem for the first time. Then stable matchings can be computed in linear time. There is a very simple algorithm which we are going to study. And all stable matchings are perfect. That is, they match all the men and the women. So these are things that are known about this problem. And I don't want you to take it face value. As we go along, we will also make sure that we prove these things. Okay, so yeah, before we proceed, One, are there questions? Second, is this a too restrictive model? That is, do you think that such models appear in practice where we had motivated this problem using students to course allocation, or hospitals to medical interns, or applicants to jobs? So what is this model capturing what we want to do in practice, or do you think it is very restrictive? How do we make it more practical? So what are suggestions? Yeah, so Mrinal has suggested that the sizes of the sets are unequal. Very good. So it is unlikely that you'll have the same number of applicants and the same number of jobs. So it is unlikely that you have the sizes as exactly the same. This is a correct practical, scenario. What else? So Ishwaran says that have priority lists. So I am not very clear what is priority list. Can you elaborate? One student may want to be allotted to multiple professors. So it means that a student wants multiple courses or multiple projects or something like that. Yeah, that is considered, that can be considered. Also, the other counterpart of this is a professor or a student or a course can take in multiple students. So these settings are called as many to many or many to one, depending on what we are looking at. So yeah, so these are valid settings where you do not restrict an applicant to be matched to exactly one post, or a post to be matching exactly one applicant, which is again very restrictive. These are natural conditions that can happen.
So by priority list, the Ishwaran here, priority list, I mean a job seeker could be having a preference to job types in an order, saying the best job he wants and the second best job he wants.
But that is what is the preference list, right? So, so this job seeker is A1. He is interested in two jobs, B1 and B2, and B1, he likes B1 better than B2. This is
okay. So that's what I meant by having a priority list. If it is
yeah. So in fact, this does encode the priority list, right?
Okay.
So sorry. So yeah. So it does encode the priority list. Yeah. Thanks for unmuting, and it's good to hear some voices also. Yeah,
Ma'am, I also had one thing. I mean, like, just to add to the Ishwaran's question. I mean, so people have a preference list, but this I just thought in a practical scenario, like if you are looking for a job and it could also happen that you're trying to avoid some kind of a job profile. So you would want to like prefer some other job over something else. So people might not give a actual preference list what they actually want. They might kind of try to, manipulate their.
Yes. So one thing is, see, if you have, if you do not like, for example, let's take it in this setting. So A1 does not like B2, right? Then a natural thing for us to allow is do not ask A1 to rate everybody, right? Because otherwise it's too restrictive. A1, by saying this, A1 is also wanting to match or wanting to get assigned to B2. This may not be the case. We are interested only in a small set of jobs. The other thing that you have raised is very valid is, can people manipulate and give? Yes, people do manipulate, and there is a large body of study about the economics of the stable matching problem. And in fact, in 2012 or 13, Roth and Shapley, they won the Nobel Prize in Nobel Prize for their work on the stable marriage, the economics of the stable marriage problem. So this is a very valid thing. In today's talk, we won't be able to touch on those aspects, but yes, people do manipulate. We would like to design algorithms that do not have where participants do not have incentive to manipulate. But we won't be able to do that completely in today's talk. We won't be able to talk about that, but yeah, there is a study about this. Okay. So yeah, so I think one of you has mentioned it is not likely that one node in a set will have priority for every node in the other set. This is what we will allow, right? So these are very natural generalizations or natural things that can come from the preference, come from practical scenarios. So the other thing Sanjeev has said is preference list should not be changed. I do not know where are we changing preferences. We are not changing. So once a participant submits, those are the preferences that are fixed for us for our problem. Okay, so assuming that the model is clear and the motivation to study this problem is clear, let's look at what is our goal in the two talks today and tomorrow. We are going to look at two variants of the stable matching problem, and we will restrict our attention to the stable marriage problem, where every A wants to get matched to at most one B and vice versa. This is not the most practical setting, but it allows us to illustrate ideas which can be generalized to the setting where we call it a B matching, or an applicant can be assigned, many applicants can be assigned to a vertex, which is called the hospital residence problem, or the many-to-many setting, which is possibly the student course allocation problem. But we will not study those. We will look at it in the stable marriage setting, but we will allow some variants from the classical model. So the first variant is what we will say, what you people have proposed is incomplete list. That is, every A need not rank all the people on the B side. So for example, A2 is not ranking B2, and that is allowed. If you have A2 not ranking B2, then B2 will also not have A2 in its preferences. So this we call as the consistency of preferences, which is natural. So the agreement should be mutual. That is, both of them are willing to get matched to each other. So that is good. So we allow these strict and incomplete lists. And in fact, just going a step further, in this example, it is still the case that the size of A is equal to the size of B. You can also allow the size of A and B to be unequal. In our example here, it is just that the sets are equal. So, but you can allow the sizes to be unequal, and that will capture one more relaxation that you people have proposed. So in such a setting also, does a stable marriage exist or stable matching exist? Yes, it exists. But of course, you cannot expect that everybody gets matched in this case. So in this example itself, the stable matching is A1, B1. This is not a matching which is perfect or which matches all the agents, because A2 and B2 are left unmatched. There is a matching in this instance, which is the other matching, which is A2, B2 and A1, B2 and A2, B1. However, that matching is not stable because that is blocked by the pair A1, B1. So you cannot have the two-sized matching in this instance, because if you want stability as your criteria. So therefore, this instance does admit a stable matching. However, the stable matching is of size smaller than the perfect matching, and it is of size 1. And again, we will just state the known facts, and as we go along, we'll also prove them. So even in these such instances, every instance admits a stable matching. It can be computed in linear time by the same Gale-Shapley algorithm that we will study, and we will also prove nice properties about it. Now, as you see here, all stable matchings in this need not be perfect. However, there is a very nice property about the stable matchings. That is, all stable matchings in this instance have the same size. That is, if one stable matching we have found out in this instance is of size 1. In fact, there is no other matching of size 1 which is stable. So in this instance, there is a unique stable matching. But even if there are multiple stable matchings in the instance, all of them have the same size. And this we will prove by a stronger claim as we go along. Okay, so this is something that is known. And stable matchings can be half the size of the maximum matching. So as we have seen in this example, the maximum matching is of size 2, the stable matching is of size 1. So you can be as small as half. And in this example, you will say, I'm just 1 off. But in general, you can think of the matching, think of an instance having a maximum matching of size 1000, whereas the stable matching is only of size 500. So you can have such instances where you can have quite small stable matchings as compared to the maximum matching. So the question in this context that we ask is, are there matchings which are larger, which have larger size than the size of the stable matching, but are optimal with respect to some other criteria? And we'll define that optimality. This, although I'm calling this as variation 1, this is the topic that we will deal later. And the second variation that I'm going to talk about is the one that we will deal first. So when we say, are there optimal matchings, already we are saying that we will allow ourselves to be not stable, because we by this known fact, all stable matchings are of the same size. So as long as you want to stick to stability, you will get the same size of the matching. You cannot increase the size. So you cannot have one matching which is of size 20, another matching which is of size 25, both being stable in such instances. So that is something which cannot happen, which is known. We will also prove that. But then the question is, can you have matchings which are optimal, but the optimality criteria may change, but they are larger in size than the stable matching? So this is the question. Any queries, any comments here? Okay, so yeah, I just saw some chat message. So the question that Prashant is asking, many to many cannot be stable. No, I did not say that. In many to many settings also, you can come up with a notion of stability. The notion of a blocking pair has to be slightly modified when we talk about many to many. So if I understand correctly, many to many, you mean the student course allocation problem. A student wants multiple courses. A course can take in multiple students. And this is the setting where you still have preferences and you are interested in computing stable matchings. Yes, you can define the notion of a blocking pair, and stable matchings do exist. Does it answer your question, Prashant? Yes. Okay. Any other question or query here? Okay, great. So now the next variant that we will be looking at is the variant where we allow two things. We allow incomplete lists, what we have done earlier, and ties. And that is why I'm introducing this as a next step, because we are already allowing incomplete lists. So what do I mean by incomplete lists and ties? So earlier we said that every participant has a strict ordering on its neighbors. Here we are allowing to have these what are called as weak preferences or ties in preferences. So when I put these brackets, it means that B1 is indifferent between A1 and A2, right? So it doesn't care whether it gets A1 or A2. Both of them are equally ranked. Maybe if it had an A3 here, A3 would be something which is lower preferred, or A1, A2 are both higher preferred than A3, and that is allowed. I mean, it can give a strict ordering intermixed with some ties, and that is something that we will allow. So this is some more relaxation in our preferences that we are giving, or some more additional things that we allow to be specified. So this is allowing ties and incomplete lists. So in such a setting, we need to redefine our notion of the blocking pair. So remember, how did we define our blocking pair? So we are given some matching M in this setting. Again, the matching is something which is a subset of the edge set, such that no two vertices share an endpoint. A pair AB which belongs to the edge set but which does not belong to the matching blocks M if both A and B strictly prefer each other to their current partners. So now this word strictly has come in because there can be weak preferences, or there can be ties in preferences. So let's see an example. So again, in this setting, stable matchings do exist. In some literature, you will also see these matchings being called as weakly stable matchings, but we'll simply call them stable matchings for our purposes here. So in this example, let's look at these two matchings, M1, which is A1, B1, and M2, which is the larger sized matching, which has A1, B2 and A2, B1. Now, we have already seen in our earlier this thing that M1 is stable. So because A1 is also, A1 continues to be top choice for B1. In fact, A2 is also a top choice. It is not surprising that M1 continues to be a stable matching. So let's verify M2. So with respect to M2, we can ask, okay, what happened to this blocking pair A1, B1, which was there? So from the A1 side, we still have this thing that A1 strictly prefers B1 over its current partner, which is B2, which was the case earlier as well. However, from B1 side, we see that B1 no longer strictly prefers B1 no longer strictly prefers A1 to its current partner, which is A2, and therefore this A1 B1 is no longer a blocking pair, and therefore it doesn't stop this matching from being stable. So therefore now this instance admits a matching of size 2, which is also stable, and a matching of size 1, which is stable. So there are stable matchings of different sizes in this instance. So this is something which is different from what we had seen earlier, where we had said that all stable matchings are of the same size, but in this case, stable matchings need not be of the same size. So are there questions here or any comments here? Okay, so the question that I see here is, in a stable matching, is it okay not to allot anything to any entity? So let's go back one slide, right? So in this example, we look at our example where there are incomplete lists, but they are still strict, and we have not allotted anything to A2, and we have not allotted anything to B2. Yet the matching is stable because we have allotted A1, B1. And if you look at any other edge which is unallotted, that is A1, B2 is not there in the matching, you ask, does it block it? No, it does not block. You ask A2, B1, does it block it? It does not block. And it's okay to leave vertices unmatched or not allot anything. And yet the matching can be stable. Okay. Any question or any comment here?
So I have a question. So the stability definition is basically partial to the fact that there are satisfied matchings, and there could be unallotted matching which is not considered as unsatisfied.
No, not like that. So first of all, I will interpret your unallotted matchings, unallotted vertices. Is that correct?
Yeah.
Okay, so let's look at, okay, so let's do the following in this example. I really wish my annotation would have been working. Okay, anyway, I will just have to, so let's say in this example itself, we do the following, that is, we allot A2 to B1, right? I mean, we just, that is also a valid allotment. So let's ask what happens if we allot A2 to B1. So you can visualize that, right? A2 is allotted to B1. Is
Yes.
it a stable matching?
And A1 is unallotted.
A1 is unallotted. Remember, in this matching we have given, it is still that A2 and B2 are unallotted, right? So we can leave people unallotted in any matching. That is perfectly fine.
So the consideration of stability is that every allotment is valid. That's what you're saying. Okay,
when you look at any edge which is unallotted, so once you compute an allotment, so let's say we computed the allotment A1, B2, right? And A1, B2 is an allotment which we have computed, or let's say we have computed the allotment A2, B1, that's all. A2, B1 and A1 is unallotted, correct? So we ask every unallotted edge that is not there in the matching, that is A1, B2. Are you a blocking pair? Is it a blocking pair? A1 of course prefers being matched to somebody over being unmatched. So A1 likes its partner, A1 likes B2 over its unmatched partner. So it is willing to participate in the blocking pair. B2 is also unallotted, so it will also be participating in the blocking pair. But more so, A1, B1 itself is a blocking pair because A1 is unallotted to B1. So A1 likes to be matched to B1 better than being allotted. B1 also likes to be matched to A1 over its current partner, which is A2. So therefore it is a blocking pair. So there are multiple blocking pairs with respect to the matching A2, B1. Is that clear?
Yeah, okay, I got it. So therefore, stability is also has to factor in the degree of blocking, basically.
So that's what I said earlier. The degree of blocking, we don't really, I mean, we don't say. So as long as you can exhibit to me one blocking pair with respect to the matching, I will say that it is unstable.
Yeah,
so,
got it. Yes.
The way it is motivated in the literature is that, okay, central authority gives this allotment or the marriage, and two people who find out that they block the matching, they just elope or run away, and therefore there is instability and chaos. So there doesn't have to be too many people to create instability. Just a pair of people who block the matching is sufficient.
Okay, thanks.
Yeah. Okay. Any other question or comment? Okay, good. So we have this, we have seen this second variation where we have said that there are two stable matchings and both of them have different sizes, which is unlike the earlier settings, the classical setting where we saw that it is all stable matchings are perfect, that is they have the same size. The second was where they need not be perfect, but they still have the same size. We have not proved these things, but we'll prove them. In the third, in this variation or the variation 2 that we are calling, the stable matchings may have different size. So what is the natural question that you would like to ask in such a setting? Where you know that there are, so an example is sufficient to show that there are multiple matchings which are of different sizes. So what is it that you would like to do in such a scenario? What can be your, yeah.
Prefer a maximum size here because all parties are allocated.
Yeah, so we don't know whether all parties will get allocated because again, you may not have the sizes equal or the maximum matching may not be a perfect matching. But yes, given that you have larger size matchings, it is better to go for the largest size stable matching, right? So the goal clearly is that if you have this incomplete and ties, incomplete lists and ties in preferences, then again the known facts are that every instance admits a stable matching. It can be computed in linear time. We will see how to do that. As we have seen in this example, all stable matchings need not be of the same size, and a stable matching can be half the size of another stable matching. Earlier we had seen that if you have stable matchings, all of them are of the same size, but it can be half the size of the maximum cardinality matching. Here there is another stable matching which itself is twice the size. For example, M1 and M2. M2 is twice the size of M1. And again, do not look at these small examples and say that, okay, this is in any way one away. This example can be blown up and you can get a large size difference in absolute numbers also. So the question is, how do you compute the largest stable matching in such an instance? So now we have set up all that we want to for our problems that we are going to discuss in today's talk and tomorrow's talk. And now we will get into the real techniques and proofs. So at this moment, I want to pause and ask, are there some things that we did not say in terms of variants? Of course, we are not going to deal with many to one, many to many. So we are not going to introduce capacities. But even with the one-to-one setting, did I omit some things that would, I mean, given this strict list, ties, incomplete, completeness, did I miss something which should have been obvious in this? I should have taken care of that. So sorry, yeah. I kept this slide to write things, but I am unable to write it here, but I'll use the whiteboard later. Okay, any suggestions? So I did not say that, okay, I did not say that if what happens if we have ties, but we have complete lists. So that is a natural thing again, right? That we still force complete lists, but I mean, at least as a theoretical question, we have ties and complete lists, then what can happen? Again, all stable matchings are perfect, and you can compute them by a simple modification to the Gale and Shipley. That is why we are not looking at that particular variation, which is also at least as a if you write them as a box, then you will see strict, incomplete, then you will pick out some of the things, then you will get 4 combinations. So one of them we have not looked at, but that is something that can be taken care. So I'm not going to talk about that here. Okay, so let's get to the real things that we want to do. So let's make sure that we are on the same page with respect to the classical model, that is strict and complete list, because that will form the foundations of the things that we want to do. So we have said in the previous variants that stable matchings can be computed in linear time. They always exist. So we are going to give a constructive proof of that, and we are going to show the properties of this well-known Gale and Shapley algorithm. Okay, so I have one question. Is it possible that the size of the stable matching is less than the half of the size of the maximum matching in variation 2? Is it okay? So Sanjeev, what do you mean by variation 2? I think you are calling it, I mean, you are asking in variation 1. So Sanjeev, are you able to unmute yourself? In the last slide. Okay, so let me go back. Okay, so in this ties and incomplete lists, yes, it is possible that stable matchings can be half the size of the maximum matching, but less than half the size. Is that what you are asking?
Yes, I am asking that the size of, is it possible that there a stable matching exists, but its size is less than the half of the maximum size? In this example, the examples that you are showing, that one matching M1, its size is half of the M2. Which is it true for all possible cases that I'm saying? This is the based on example here.
Okay, good, very good. It's a nice question. So your question is, can the maximum, in general, can the maximum matching be of size 100 and the stable matching is only of size 25, right? I mean, strictly less than half the size of the maximum matching.
Yes.
Yeah. So the answer is no. The stable matching has to be at least half the size of the maximum matching. And again, we will see a reasoning why this happens to be true. Okay, it's a very good question. We will come to this possibly towards the end of the talk, right? Yeah, but this cannot happen that the stable matching size is strictly less than half the size of the maximum matching. And okay, so the short answer is that stable matchings have to be maximal, and maximal matchings are at least half the size of the maximum matching. So if people have seen maximal matchings, then they will understand. If they haven't, we will see this proof when we come to this. Okay. Does it answer your question, Sanjeev? Okay, great. Okay, so we'll come to this classical model, and we will look at this very simple but very elegant, as well as having very nice structural properties, the Gale and Shapley algorithm, which is called also the proposal algorithm, where one side of the bipartition proposes and the other side rejects or accepts based on the proposals that it gets. And we are going to run it from one side. It is the side that we choose, it doesn't matter. And we will see what happens when the sides differ, and is there a difference? So what happens with respect to different properties about this algorithm. So in this case, we will call the A side or the men side as the proposing side, and the women as the accepting side. Okay, good. So what happens? A1. So if you are observing keenly, then you will see that the highlight on the preferences is changing. So you see that B1 also is being highlighted with the proposal that the vertex is getting. So this A1 is proposing to B1, and since B1 has nobody currently, B1 will accept the proposal, and that we are writing by accept and also by the square that we are showing. So this is a tentative acceptance that B1 has given. Now A2 proposes to B1, and we see that B1 now gets another proposal, which is highlighted here, which I hope it is visible. And B2 now evaluates its proposal between, it has already tentatively accepted a proposal from A1. And then it says that, okay, I have a weaker proposal, so maybe I'll not accept it. So this we will call it as a reject. So A2's proposal to B1 is rejected. So A2 goes ahead and proposes to the next person in the preference list, which is B2, and this gets accepted. So this is how the proposal algorithm works, and it terminates at the time when either everybody is matched, which happens in the case of strict and complete list, and when the bipartition is complete, or the case where some vertex may not be matched, but it has exhausted its preference list by proposing to every person in the preference list and possibly getting rejected, because if it has not been matched, then it must be rejected by everybody. So the algorithm stops when there are no more proposals to be made. And why do we call this a linear time algorithm? Because it goes once over the edge set. It goes at most once over the edge set. Therefore, we do not, it's just going over the edge set. You require a little bit of work to make sure that you can accept and reject proposals by keeping some data structure, but that is not difficult. So you can do that, and you can make sure that the algorithm can be implemented in linear time. Okay, any questions about the Gale and Shapley algorithm? Okay, so what is it? So once you write an algorithm, what is it that you need to do? You have now seen several things. So what is it that you need to do as soon as you write an algorithm? So in this case, everybody should get a partner. Yes, in this example, everybody gets a partner, but in general, everybody may not get a partner. Okay, so yeah, any algorithm do you write? If you write, what should you do with respect to that algorithm? So this is a school on theoretical foundations of computer science. So okay, good. So we should try to prove that the algorithm is correct. So first of all, that we should prove that the algorithm terminates. That is, it is indeed an algorithm. That I hope it is clear that every A proposes to a B in its preference list at most once. So therefore, there are maximum cardinality of E many proposals, and therefore the algorithm does terminate. It never goes back and revisits the same proposal again. So therefore, it is indeed an algorithm, or it does terminate. Now, can we say what do we mean by correctness? What is the meaning of correctness in this context? Yes, we need to prove the correctness. What is the meaning of correctness in this context? Good. So the matching is indeed stable. Very good. So how do we prove that the matching is indeed stable? So at this stage, I'm going to stop the this thing and go. Okay. So it just shows that MS is the matching that is produced, and it in this example, it is indeed stable. I would like you to observe the following things. That is, I never said during the mentioning of my algorithm, how do we choose who proposes next, or how did I choose A1 to be the one who is proposing first? A2, maybe I should have chosen A2, and maybe when there are n people, how do I choose one? And suppose I select AI to be the one who is proposing. AI proposes to BJ. BJ rejects somebody. Now should I choose AI plus 1, or should I choose the one who is rejected? How does it affect the algorithm? So I never mentioned this. So what happens if I do proposals in different order? Does it matter? What does it mean to matter or not matter? So Any thoughts on this? And the second thing is the side which proposes does matter. That is, it does matter which side is proposing. Again, what does it mean by it does matter? So any answers to these questions? So what do I mean by the order of proposals does not matter? Similarly, what do I mean by the side which proposes does matter? Okay, A1 can go before A2 and vice versa. Okay, that is the order of proposals. But what do I mean by order of proposals does not matter? Okay, if A proposes to B, then A gets the best possible match. Is that correct? Okay, so what do you mean? Okay, so let me just state these statements in a more formal way. So the first thing that we have said during specifying the algorithm is we have left the order of proposals unspecified. So irrespective of that, we want to show that this algorithm produces a stable matching, right? That was one of your claims that you want to prove that it is correct. Now the question that I have is, suppose I prove that the algorithm is correct, that it, irrespective of what the order is, it will always produce a stable matching. When, let's say I have a large instance, I have many A's, A1 to A100. I let people propose in different orders. So I choose a particular order and I always follow that. You choose another order because I never specified that and you follow that. What do you expect? Do you expect you will get different stable matchings? Do you expect you will get some? What kind of expectation do you have? Is the question clear? Okay. Okay, Rajat has responded. Okay. What do you mean by same, Rajat? Okay. I will wait for your response. Same matching. So Rajat says that irrespective of the order in which the applicants propose, you will still get the same matching. Very good. So if this is the case, you also would like to prove it, Rajat. Do you know a proof of this? Have you seen a proof of this? Okay. So is this your guess or you have observed it in certain... Okay. So same, Brinal also says same matching. So I would like to understand where is the intuition coming from that you will get the same matching.
It's something like even if, let's say, currently we do not have like a perfect match, and the person like let's say in this case A2 and B1 got matched. Eventually, when A1 proposes, it will be replaced, and A2 will have to propose again.
Okay, but this is in this example, right? I mean, in this example, yes. So this example is possibly giving you an intuition that if you let the order be A2 and A1, you will still get the same matching, which is shown here, which is MS, right? That is what you are saying. You tried it out on this example. Is that what you did?
Yes, ma'am. Like it's something like eventually the stable matching will be the same irrespective of the order. On
Yes.
this, yeah.
Yeah, but good. So if you claim that, you must prove this on any arbitrary instance, right? Without taking some examples. Yeah.
Yeah, ma'am.
Yes.
Yeah. So my intuition was that, like, irrespective of the how we take, like everybody has the priority list, right? So that order will be always followed, and the B side is always waiting for the best response. So irrespective of the order, that doesn't matter. So you finally end up with the same pair of people getting matched.
Yeah, the intuition is correct, but this is not a proof. I mean, this is not a proof. The intuition is correct. We will see a proof of this fact, but the intuition, actually the claim is correct that irrespective of what happens, you will get the same stable matching. Okay, so yeah, any other comments or questions? Okay, so before I go to this, the order of proposals does not matter. Let me just show you this example where, again, I plan to write it down. Therefore, I kept the slide blank. So if you see this example, the example looks similar, but it is different from the earlier example. So in this case, A1, okay, so let me try to write this example. A1 has B1, B2, and A2 has B2, B1 as its preferences. I'm using these commas to show that it is a strict list. And B1 has B1 has A2, B2 has A1, and A1 and A2, right? Okay, so let us view this example and see what happens if we run the Gale and Shapley from the A side. So we will have A1, B1 followed by A2, B2, and there are no rejections, and therefore this is the stable matching. So this matching is stable in this instance. Of course, this is by inspection. We haven't proved that it is stable, but in this by inspection, you can check that there is no blocking pair. Now, if you run the proposals algorithm from the B side, then you see that B1 proposes to A2 and B2 proposes to A1, and the matching, that is A1, B2, A2, B1, this also is a stable matching in this instance. So what this example shows is that if you change the proposing side, then the matching may change. However, both the proposing sides will lead to different matchings, but they will be stable. By the way, we will prove it now. So what we have seen is by a simple example that there can exist multiple stable matchings in a given instance, even if there are strict and complete lists. Okay, so having said that, I will now, what I will do is first we will show that the GS algorithm, this is the Gale and Shapley algorithm, produces a stable matching. Right? Okay. So, so to show this that it produces a stable matching, let us say that it has produced a matching M, and let us say that there is a blocking pair AB with respect to that matching. So if AB is a blocking pair with respect to that matching, then this edge does not belong to the matching, but A prefers its current partner, A prefers B over its current partner. So let us have a current partner for A. A can also be unmatched, but we will not take that condition. Similarly, B prefers A over its current partner. Now let us ask, how did we lead into this situation? How did we get into this situation? Let's assume that A side was the proposing side. So what had happened when A side was the proposing side? This little A had proposed to everybody in its preference list. And if in particular it got matched to this B prime, then A had proposed to everybody higher preferred in its preference list and got rejected. So when this B rejected A, B must be having a proposal or a proposal from somebody higher preferred than A. That is why it must have rejected it, or it must have gotten it later and it rejected it. And the B, the side which is accepting or rejecting, its partners get only better and better. So at that time, if it had a better proposal, it gets only better and better as the algorithm progresses. Therefore, if A had got rejected from B, then B's partner cannot be lower preferred than A in the preference list of B. It should be higher preferred at the time of rejection and eventually at the termination of the algorithm. So irrespective of how the proposals went ahead, it must be the case that there cannot be a blocking pair AB with respect to the matching that is produced. So is this proof clear? That is, the GS algorithm produces a stable matching.
Ma'am, so at every point in the algorithm, it's the matchings obtained so far are stable, right? Like completely stable, right?
do you see that it need not be stable throughout the algorithm? It is only stable at the end of the algorithm. So somebody had this question, right? Hello?
Hello, ma'am, it was me, yes.
Yes. So is it clear to you that it need not be stable throughout the...
So I'm talking about like provided A2 did not come at all into the picture, like
How do you say that it? How did you say that A2 did not come into the picture? We have said that the order of proposals we don't know. So A2 can propose to B. So is this a valid instance? I mean, okay. So there is only one here. I mean, there's only one, the top choice. So this is a valid instance, right? So let's say A2 proposes to B1. What happens? It gets tentatively accepted, but A2 B1 is not a stable matching in this instance.
yes, ma'am. Yeah.
Okay. So you cannot say that it is always stable, right?
Right. Yeah. Only at the conclusion of the algorithm it's stable.
Yes, yes, yes. Okay. Okay. Any questions here? Okay. So I am going to skip the proof for now for the fact that the order of proposals does not matter because I think I'm running a little slow. So I'll just go ahead and not talk about this for the moment and then go back and talk about it if we have time. Okay, so this slide has an incorrect example, but we have seen an example on the whiteboard where we have seen that the order of proposals does matter. We have not seen that the order of the side of proposals does matter. The order of proposals does not matter. We have not seen a proof. Okay, so now what we have done is in the classical setting, we have seen an algorithm to compute a stable matching. And this algorithm essentially can be used for computing a stable matching in variation 1 also by simply saying that the lists are incomplete and but they are still strict. So you just go ahead, and this can be used even in the case where you have unequal sizes of men and women, and the same algorithm will work with the same proof that it computes a stable matching. Okay, so we are going to come to variation 1, variation 2, where our goal is to compute a matching which has compute a stable matching in the case where there are incomplete lists and ties. Now, when we say incomplete lists and ties are there, we can have general incomplete lists and ties. That is, ties can be there on all sides, I mean both the sides. But for the moment, we are going to assume a restriction, that is only women or the B side can provide ties like it is shown in the example. That will simplify the analysis, and because we want to illustrate an approximation algorithm. Okay, good. So now we have already seen that it can admit multiple stable matchings of different sizes, and our goal is to compute the largest stable matching in that instance. However, this problem is NP hard even under very restricted settings. In particular, this setting that we are talking about, that is the ties are only on B side, and in fact there are more restrictions on ties, and yet it remains NP hard. So I hope you understand what it means by a problem being NP hard. That is, unless P equal to NP, it is unlikely that we are going to get an efficient algorithm for this problem in general cases. So what is our resort? You have already seen that one of the ways to handle NP hardness is to talk about approximation algorithms, and that is what we are going to do in this talk. We are going to give a nice and simple approximation algorithm to this problem, which will also allow you to connect what you have learned about approximation algorithms in the earlier lectures. Okay, so a simple and naive method is to break ties arbitrarily. That is, you break these ties in different ways. And in this example, there is only one tie. That is, B1 says A1 and A2 are the two people tied in my preference list. I try to break it in the different ways that is possible. This is a tie of length 2. Therefore, there are only two ways possible. That is A1 followed by A2 in the strict order, and then A2 followed by A1. Because recall that B1 doesn't care about which one comes first. So therefore, it is equal for it to say that A1 comes first or A2 comes first. So in general, if you have a tie of large length, you will have different variations. Also, when you have multiple bees having ties, you will have to try out several combinations. So this is not an algorithm that will lead to polynomially many instances. So this we cannot try out. If we try out all possible breaking of ties, then we will of course get and choose the largest amongst that, we will of course get a stable matching, but we cannot do that in polynomial time. So therefore, what we are going to do is break ties arbitrarily and run the Gale and Shapley algorithm. So, this method does not lead to the most lead to the largest size stable matching, but it will lead to some stable matching. And we would like to see, can we improve on this naive algorithm and get a good approximation to stable matching. So the first thing that is there is that even if you break ties arbitrarily, that is, you just do the simplest thing that is possible, break ties arbitrarily and run the Gale and Shapley algorithm, you will still get an half approximation to the size of the maximum matching. And this is by the fact that stable matchings are maximal and therefore they cannot be small. The question that was asked in the initial part of the talk, they cannot be strictly smaller than half the size of the maximum matching. And of course, stable matchings are no larger than the size of the maximum matching in the instance. Therefore, any stable matching is going to be at least half the size of the maximum matching. Therefore, it is already a half approximation or 0.5 approximation to the maximum cardinality stable matching in this instance. So therefore, this result is what we call it by folklore. I mean, it is a simple observation that one gets. Now, what after a series of works, Irving and Manlow, or I mean, with quite a bit of effort, they with an involved algorithm, they came up with an improvement which is 0.6. That is, you will have a matching which is at least 0.6 the size of the maximum size stable matching in that instance. And this, I mean, as you see here, right, the different black colored values are progressively increasing towards 1. The red colored values say that there is a hardness, that is, you cannot get a 1 approximation in general. That is, you get something which is optimal in general, you cannot get. This is the NP hardness result, what we talked about. But there are also results saying that you cannot get better than 0.9. So you cannot hope to get as close as possible to 1. And these are hardness results. We are not going to go there. What we are going to do is discuss something which is in between, which is this 0.66 approximation algorithm to the maximum cardinality stable matching problem. So why did I give all these things? For you to get a context. So this problem has been studied, and even as recently as 2 years ago in 2019, Lamb and Plaxton have improved it to 0.73. So what is the holy grail for any of us in the theory community? To bridge this gap, that is, say that there is some X approximation algorithm and you cannot get any better than X. So X minus epsilon is not possible. So we always try to bridge this gap and say that these two are as close as possible. The red and the black, in fact, they should be 1, then it will be very nice, but we may not be able to get there. Or sometimes we fail to get there. Sometimes we are very close, but we still have gaps to close. So this is the state of the affairs for just assuming ties only on B side. Of course, when you allow ties on the general side, the results are slightly weaker, but there is a series of results. Again, I'm not going to state them here. Okay. Any questions or comments about this part?
Ma'am, I have a question, ma'am. This NP hardness, is it NP hard only to obtain the largest size stable matching?
Yes, it is NP hard to compute the largest size stable matching, because computing a stable matching is easy. You simply break ties in an arbitrary way and run the Gale and Shapley algorithm. It will give you some stable matching, right? So in fact, as I said, it will not only give you some stable matching, it will always be at least half the size of the stable matching. but you cannot guarantee any more than half, because as you have seen in the previous example, if you break ties in the wrong way, that is you break as A1 and A2, you will get a one size stable matching, which is exactly half the size of the two size stable matching, which is the maximum cardinality matching.
Yes, ma'am.
Got it?
Yes, ma'am. Thank you.
Yeah. So what this means is, if you say that it is 0.66, in every instance you will be guaranteed that you will be 0.66, at least 0.66 times the size of the maximum cardinality stable matching in that instance. At sometimes you may be optimum, at sometimes you may be so even in this case, right, if you break the ties as A2 A1, you will be optimum, but you cannot guarantee that by this nice tie breaking strategy. Yes, so this is our goal. That is, we are interested in computing this matching, which is 0.66 times the optimum in every instance of the stable matching problem with ties and incomplete lists, but ties allowed only on the B side. That is, only participants on the B side can specify a tie. Okay, good. So now the algorithm is due to Kiraye, and it is a very simple and elegant algorithm, and the idea of this algorithm has been used at multiple places. That is why I like to present this algorithm. So what does the algorithm say? Break ties arbitrarily, run the Gale and Shapley algorithm the way we are familiar with, and after this, unmatched A's propose with increased priority. So we are going to see what this means by running it on an example. Okay, so so when unmatched A's propose with increased priorities, B's also have to decide what to do when they get such increased priority proposals. B's use this increased priority for breaking ties. So we'll see this. I mean, these two lines may not be very clear. We'll see this in an example, and we'll ensure that stability is never violated. Okay, so let's do this in our example. This is our standard example now. So we break the ties arbitrarily, but we break it unfavorably for us, so that Gale and Shapley gives us a one-sized matching. So let's break it as A1, A2. We know that the Gale and Shapley is going to give us the one-sized matching, which is okay. So this is the end of the execution of the Gale and Shapley. A1 proposes to B1, it gets accepted. A2 proposes to B1 and it gets rejected. And A2 has exhausted its preference list, so it is going to stop and do nothing. And this is the output of the Gale and Shapley run. So this ends the Gale and Shapley run. Now is where Kiraye's idea kicks in. It says that unmatched A's propose with increased priority. So who is an unmatched A? A2 is an unmatched A. So A2 proposes with increased priority and says that I will show this in the slide by saying A2 star proposes to B1. So if A2 star proposes to B1, B1 asks, okay, what is my current partner? My current partner is A1. Was I in a tie with A2, with A1? I mean, was I in a tie with this? Yes, I was in a tie. Then I will use this increased priority to accept it. If it were the case that I strictly preferred A1 over A2 in my original preference list, I will do nothing. Is this clear? So what do unmatched A's do? Unmatched A says, I will propose with increased priority. This increased priority is denoted by this star that I am showing here. Whenever a B gets a proposal from any A, it looks at its partner and asks, okay, what is my current partner? My current partner is somebody. Was I in a tie with the proposer and this person when I had my original preference list? Don't worry about this breaking ties, because that breaking ties is something that we have done to run Gale and Shapley. So was I in a tie? If yes, I will accept this increased priority. Otherwise, I will simply reject it. If I have a strictly better partner, I don't worry about it. And this continues, because in this example, it will just stop very quickly after this. So A2 star proposes to B1 and it gets accepted because A2 and A1 were in a tie. But now A1 is left unmatched, right? So A1 says, okay, I am unmatched. Why should I not go and propose further in my preferences? Note that there is no increased priority. It has not even proposed everybody with its original list in the original list. So it goes ahead and proposes to B2, and then B2, because it is unmatched, it accepts it, and this is the final matching, which is A1 B2 A2 B1. So this is where we have our matching, which is A1 B2 A2 B1. Is this algorithm clear, or are there questions?
Ma'am, can it so happen that like among the unmatched A's, there happens to be ties, and how do we have priority in that case, ma'am?
Good. Okay. So let us say that. So what Kiraya does is to give this thing is, so think about this as giving real numbers to these vertices, right? So when you say that you have A1 at rank 1, you in fact rank it in the other way. That is, you give priorities in the inverted way, that is 2, 1, 3. I mean, so you just rank it in the other order. That is, higher ranks means better, higher numbers means better priority, right? So you rank your ordering from K minus 1, K minus 2, and so on. So when you give this star, you just give a 0.5 increase in priority, which says that you are just better than your tied partner, but no better than your strictly preferred partner. Do you understand this? So therefore, when you have two people who are unmatched and they were in a tie, both of them get the same this thing, so it doesn't change. So remember that if you get something which is of the same priority, you don't change your partner just for the sake of it. You just discard that. Is that clear?
Yes, ma'am. So in that case, like the order of proposing would, the order of proposing will matter, right?
Order of proposing will matter for the matching that is output, but so we have never said that the order of proposing does not matter in this case. Yeah, the order of proposing will matter in terms of the final output. Yes.
Yes, ma'am. Got it. Yeah.
Yeah. Okay. Any other questions? Okay, so what I'm going to do is, we want to argue about the size of the matching. Okay, so I would like to ask the organizers. So how much time do I have?
5 minutes, I guess. 6 minutes.
Sure.
Yeah.
Okay, sure. Yeah. So I'll see how much I complete. Otherwise, I will leave this. Thankfully, I have it pending. I have another class tomorrow, so I can take it tomorrow. But I'll try to see. Okay. So to show that we have in fact the size of the matching, we want to show that we are a good approximation to the maximum size stable matching in the instance. So we want to argue that the size is 0.6, at least 0.66 times the size of the maximum matching. And where is this 0.66 coming? It is at least 2/3 the size of the maximum cardinality stable matching in the instance. So now what we are going to show is talk about augmenting paths with respect to matchings and say something about augmenting paths. So we want to show that with respect to this matching that we have produced, there are no short augmenting paths, short meaning short of length 1 and 3. So I'm going to talk about augmenting paths which are defined even when there are no preferences. And I think I'll just talk about augmenting paths and complete this last proof in the class tomorrow. So, okay, so just to get a sense, is everybody very comfortable with augmenting paths and the theory of augmenting paths and so on? Can people quickly say yes, no? Okay, nobody is saying anything. Okay, so let us say that we have a bipartite graph. We have the underlying edge set, which is denoted by the black edges. There is some matching that is given to us. This is the matching is shown by the red edges. And we are interested in knowing, forget there are no preferences. So is this matching of the largest size? That's all we want to know. So the question is this matching of the largest size? There are 4 edges that are matched. Is this matching of the largest size is the question. Remember that every graph need not have a perfect matching. So this matching could as well be the largest size matching. So is it the largest size matching in this instance? Or is there a larger size matching? So anybody?
This is not largest size, I think. A3 can be matched with B5 and A2 can be matched with B1.
Here your first thing.
A2 with B1.
A2 with B1, okay.
And A3 with B5.
A3 with B5, right? Okay, so you're unmatching this edge, right? A3, B1. You are saying that delete this matched edge and now add A2, B1 and A3, B5. Is that right? Yeah. So what I want you to observe is what he did. I don't remember who said this, but this is a correct thing. It is not a largest size matching. There is a larger size matching, which is of size 5. But what I want you to observe is there is no way in which you can simply add edges to this matching. You have to delete an edge and then add an edge. And this process is called the process of augmenting the matching using what is called as an augmenting path. So what is an augmenting path? An augmenting path is a path which is a collection of edges such that it starts with an unmatched edge. It has a matched edge, again an unmatched edge. That is why it's an alternating path with respect to the current matching. So the alternating path is shown here, that is A2, B1, B1, A3, and then A3, B5. So this is an alternating path with another property that both the endpoints are free. That is, they are not matched with respect to the matching. And therefore, this path can be used to increase the size of the matching by 1. What is an alternating path? An alternating path is a collection of matched, unmatched edges, which is a path in the original graph. An augmenting path is an alternating path, which also has this additional property that both the endpoints are free with respect to the current matching. And alternating and augmenting paths are always described with respect to a given matching. So if the matching is empty, then any single edge forms an alternating path, which is an unmatched edge because the matching is empty, and it is also an augmenting path because it has both its endpoints free. So when I say free, they are not matched with respect to the matching. In our old matching, the only free vertices were A2 and B4. All other vertices are matched, so they are not called as free. So what property the augmenting paths have is, augmenting paths always have odd number of edges. So they have lengths like 1, 3, 5 and 2k plus 1. And if a matching does not have any augmenting path, then it is called a maximal matching. And maximal matchings are always at least half the size of the maximum matching. This is a proof that I would like to do, and we'll start the class tomorrow with this proof. And in general, if you have a matching without short augmenting paths, then it is a good approximation to a maximum matching in any graph in general, in particular in bipartite graphs also. So this is something that we will use in tomorrow's class to complete the proof in the first 10 to 15 minutes to show that our matching that we have produced by Kiraya's algorithm is indeed a good matching to good approximation to the maximum size stable matching. So I think I have run out of time. I would have liked to complete this, but anyway, I think it's more important to go at the pace of the class. So I'll stop it here and complete these things in tomorrow's class. I'll hold on for any questions or queries that people may have.
Ma'am,
Sure.
this notion of augmenting paths, it's applicable in general graphs or only applicable in matchings?
So see, augmenting paths are always defined with respect to a matching, but they need not be only in bipartite graphs. They are also in general graphs. General meaning non-bipartite graphs where you allow odd cycles. So remember, we are talking about these matchings without any preferences. There are no preferences. This is general bipartite matching. I mean, we are talking about it in the bipartite setting, but this is true even in the case of general graphs.
Got it, ma'am. Thank you.
Does it answer your question?
Yes, ma'am. Thank you.
Yeah. Any other question or comment?
Ma'am, there is a question in chat.
Yes. What is the current thought of moving to 0.9 in current research? So you mean that what do you mean by current thought? So as I said, I think this is the latest that this slide, whatever it had, right? This is the current state of affairs. So you are asking what is the intuition? Is this the correct answer or is this the correct answer? Is that what you're asking?
Is there a possibility in the current research of moving towards 0.9? Is there any indication? What is the current awareness in this domain?
Yeah, so I mean this progress, right, has been slow and also quite laborious in terms of, I mean, there has been a lot of techniques have been used to get to 0.73 and so on, right? So I mean, I do not know whether, I mean, the improvement is slow and it may be possible, but I cannot comment that. I mean, I don't know whether it will necessarily go to 0.9 or the lower bound is nearer to 0.73.
Okay, thanks.
Thank you, ma'am, for the informative and interactive session. We will have our next session on parameterized streaming algorithm by Professor Saket at 2:30 p.m. And we'll see you all there.